Okay, we are going to discuss about how to create model using cell model or surface model, and then after that we run the analysis, and then we assign cell element to the model, to the surface model. So we start create by creating part here, and after that start to do the sketch. Okay, then let me start to use the same model that we have constructed previously, this 100 millimeter, and after that we make a construction line that can help us to identify whether we already have a correct dimension or not. Then after that, here about 500, let it be more extend, and then after that we create the corrugated from this point here. Let me use yesterday we used 60 degree, so 60 degree, and then the first highlighted box there, 92.734 millimeter, so it is the length of the length of the line. So let we make it 100, and after that, to access the angle, we press tab button. You can see there, oops, you can see there we have highlighted the angle, so 90 plus 60, so if 150 degree, and then we enter. So then we have this line, and then the dimension here is basically the constraint. This is the way the what you call it, Inventor works. So then it's basically a parametrical modeling, yeah? So we can set dimension, and then when we do modeling, we adjust the dimension, so everything will be modified. So then we delete the line that we don't need, and then trim here, and then trim this line. So we already have this one. Let me check this line with the dimension of this line, or we just simply click and 200. So we need 300. Sorry, this is 100. Oh, so this was 100. So then, so this one is 200. Supposed to be. This we already have the slanted point there. Then 200. Enter. Escape. Then we copy this one. Transfer this one is not, the constraint will not and then we copy this one, and then select the point where we'll move, copy this one, and then done. Then we construct, actually I want to do mirroring. Here we mirror the select this line, and then select the other one, press shift button and select. After that do mirror, select the mirror line, and then apply. Done. So we delete the other line. So then we already have this full wave, full corrugated. Then copy copy, select this one, and then this one, and escape. Check the length from this point to this point. It's already more than 1 meter. It's okay. So then we use this two wave or two corrugated shape here. Then we weld or join on these two segment by select all, then right click, and then sketch doctor, and then do diagnose and okay. Actually, I don't know the other method to weld the line. That's not in here. And then after that, we do next, and then there is a treatment given is combine sketch point, then finish. It will ask you, would you like to combine the highlighted sketch point? Yes. And then yes, and then yes, and okay. So then the line will be in one shape, and then we finish the sketch. Okay, and press the home icon there, then we do extrusion. So then you can see there is all the line, multiple line convert into one single line, and then 1001 meter, then okay. So to continue construct the stiffener and also the the flanks, so we can do 2D sketch. We select this one, before that we escape to cancel the command, and then we set the plane first, the working plane. Select this one, and then just simply this required two line, so then that one, and then you can see there is 90 degree from the selected face here. So we select the line, and then after that we select the face. So then there is a degree, 90 degree here, and then okay. So then we constructing this working plane here. So then after that we do the sketch, and then select this working plane here, highlighted work plane 1, select. Okay, then so then we would like to check first where it is. Like better we back to this home, and then we want to have what we call it, this one is 100 millimeter, and then it's 200 over there. So then so we create this point, and then better we move to this is front, and then move to the left. Okay, so we would like to have point here is a construction line, 100, and then here from this point I create 1000, 200. So my flanks will be 300. So why I select create this line, because by having this I can create a rectangle. Click here, and then end to here. After that click here, click there, and then end here. Then like that, and then I can do finish this one, and then to create the surface here, use the patch, select these two patch, click, and okay, then it's convert into what we call it, surface. Okay, then same process, we set the plane to this line, and then about the surface 90 degree, yes, there. And after that we go for the surface. So then since at the back we already have the shape, so we can do sketch here, and then we have to start the sketch first. Sketch, press this button, and then working on this surface, work plane 2. Okay, then we do projection. We project this line, or we project the node only is okay, and then node here. So then we create a rectangle, same as previous one. So you can see there is a projected node here, helping us to create the rectangular. Click here, and then here to this projected node. Escape to end the command, and then finish the sketch, and then 3D model we use the patch. Select this one, and then okay. So it's created already, and then after that we create the flange. Create the plane, click there, and then 90 degree to the vertical surface, and okay. So after that we start sketch on this work plane. Just simply create a rectangle here and here. Finish, and then same process, patch. Okay, then return back to we go here and then to the bottom. So better we view like this, and then after that we set the plane this line, and then the surface 90 degree. Okay, then after that we start the sketch, and then we create a rectangle from this point. That one, and then finish. After that we do patching, select them. Okay, so then basically we already have the shape, the surface model, and then we height, the visibility of the work plane. So we have this one. So then the model already is already completed, and then we go to the Nastran analysis. Go here, and after that first we do linear buckling analysis. Option, take 3 modes, and after that we need to assign material, and then material here we have under the model we expand the this one, then edit the generic one here, select material, and then press S to access the S, and then to select S275 and OK. So name S275. Okay. Let's say we want to have S275 for the web, and then S355 for the stiffener and the flanks. So we add another one, new. Select material, Autodesk material, press S, go to the S, and then S355. Okay. Same goes to the here, and then okay. So we have this one. So for the idealization, it is not as direct to the solid model, so then we need to use this one, the cell model. So we do create new cell model. So the thickness we can assign. So let's say the thickness of the flanks 30 mm, and then we want to use the S355, and then select the associate geometric, and then select top here, and then top here and bottom. So we have these two, and then okay. So this one using the quadrilateral cell element, or you can also select the triangles, and then press OK. So then after that we select new thickness for the what to call it, the stiffener. We put it 15, and then S355 associate geometry we select. Also we use the quadrilaterals, this one, and OK. This one new for the web, corrugated web, say 6 mm, and S275 associate. This one we select, take, just click, and then rotate, orbit, this one, and OK. So we have 3 cell element. So then after that we can do meshing. Right click, and then, or you can press edit here, and then by default it's calculated based on the area that it has, so 68. So if you want to increase later on, you can do. Basically we need to do a convergence study of the meshing, numbers of mesh, the density of mesh. So there is a what call it, we start from the minimum one, and then after that continue to the what call it, the numbers of the mesh, that when we apply, it will not change a lot, and between two different numbers of density, mesh density. And then we select this one, continuous meshing, so then in between for solid only merge nodes on perimeter, but for the cell it will continue, but for solid it on the merge, only merge nodes on parameters only, so then it's not change the what call it, the mesh. Then we can generate the mesh. You can see here, so since we select the continue, so just like this, continuation. So and then OK, then after that we assign the load. Right click, new, and then we select the magnitude is in Newton. Let's say we use only 1000 kilonewton, because in local linear buckling the result that we will get is the eigenvalue. So to the so basically the what do you call it, shear capacity is determined by the multiplication of the eigenvalue and the applied load, or magnitude of the load that applied, and then negative downward force, and then entities to here. So then and then OK. So then we can see the direction of the load downward, and after that constraint, new constraint. The first one we to ensure this one at the top here, I mean so basically if you can manage to have a different way, I mean assumption to construct your model, or to assign the load and then the support. So the less support condition, so somehow your model will not stable, so it will give you a very long calculation, or maybe failure or error, something like that. So then we assume here, we assume that there is a what call it, restriction on about x-axis, and about y-axis release, and then about z-axis translation is avoided here, resisted. So all the rotation is allowed, and then the entity here. So then you can change basically here, or let's say you free the translation about z. So then because of the eccentricity, so then the what you call it, it will rotate lateral. There is a torsional will occur. Then okay, then here, then constraint new for fixed. So in this case, you can also put fix here, or you can put a pin along the line here. Entity, I select this one. So I pretend, or assume this one as a what call it, cantilever. Okay. So then here, so basically we already have everything. Then we run the analysis. Okay. Here, let me put here the name here as shell girder, shell girder, and then save. Yes. Let's run. So it's faster than the solid model. And then the degree of accuracy you need to check that one. You need to compare. So then we have here 5100 for the what you call it, for the eigenvalue. So multiply by 1000. So then you have 5000 kilonewton, basically 5000 kilonewton of the shear capacity, buckling capacity. And then we check with the linear nonlinear analysis. So here we go to linear let's say we already have this one. If you want to change, what you can see here, the stress it's not, it is not reached even the what you call it, the yield strength 175 already buckle. The maximum stress here is 175. Then we can create another what you call it, new analysis. We go to this one, part 1 here, and then new analysis, and then we select what you call it, nonlinear static. Make sure here large displacement on. Okay, and then the contact by default bonded, because we don't have any what you call it, any contact, any part. Then here nonlinear setup here, number of increment, let's say is 10. Then intermediate output on. So then every what you call it, every increment it will generate output, deformation, and also the stress. Advanced setting, set auto here, and then load the convergence we set it 0.1, and then maximum bisection we set it to 50 or 40 or 50, and then okay, and then okay, what we check here, where it is, or okay, anyway, it's already used the same, no need to change. Then mesh model here, we can directly generate the mesh. Oops, sorry. So maybe the idealization is not assigned. Idealization is not assigned. Cell mesh model. Wait a minute. Continuous meshing. Setting, generate mesh. No idealization. Oh, no idealization, because I okay. Let me do idealization. This one idealization belong to what you call it, the previous this one. Anyway, we do the nonlinear. So cell number 4. So we edit here. This one for the okay, assign the thickness 30. S355. Anyway, so we have to set this one. Okay, and then after that create another one. 15 S355 associate as the surface. Okay, and then cell new, as you can see there, generated S75 associated, and this one is 6. 1 2 3 4 5 6 7 8 and then 9, and okay. So before we continue, we have to change the material here for add the nonlinear elastic plastic. We set at least 5% instead of 10%. Use 5% here. Okay, and okay. Then for the 5 as well here, nonlinear on. Okay, already done for the 355 S75 S275. Make it nonlinear, so elastic plastic 5%. Okay, yeah, you can refer to Annex C of Euro Code 3.15 for a more detailed selection of the what you call it modulus plastic. And okay, so then after that we can create the mesh. Right click, generate mesh. So because it's already done, or we have to continue meshing and then generate mesh. Done. Okay, then the load, right click, new, how much load that we need to apply. So then based on the what we call it buckling capacity that we have, it is 5,000 kilonewton, right? So then put it 10% of it, 5,500 kilonewton negative to where? Here, downward. And then load and constraint new here, we release all this rotation and translation about Y into here. Okay, then another constraint here, fix, put it here, and okay. So basically we already have all here. Then we run the analysis. So increment number 1 already completed, 2 completed. Keep increasing. 75, 91, 8. I think it's still what call it, linear. 152, 152. Then okay. So we can increase the load. Let me see the increment. Let me check here. Maximum displacement. Is there any? It's still what call it? Still linear. So then we increase the load. It is okay to start small. Anyway, previously we detect that buckling capacity is 5,000 kilonewton, more than 5,000 kilonewton, right? So let's say we put it 700, and then okay, then we run. And then remember that the maximum yield is 179 megapascal. So it's 149,170. So maybe 150, 213 is not yield. Okay, let me check. Somehow It is due to still maybe still smaller. Let me change the it's more than 1000, so then it's more than I mean what do you call it, the yield strength will be, I mean the nominal yield strength will be exceeding the 275. Okay, previously we got 250, right? Then run the analysis. Hopefully we can see the non-linearity started on about increment number 8. 1 to 152 7 8 still not 274 10. I think this one already 9 already. There is a what call it non-linearity. Displacement, check, there is 9. So it's about 0.9 0.9 of 1900 kilonewton start to what call it deform non-linear. So let me increase one more time. Sorry. Anyway, if we want to what call it see how the deformation of the shape deformation shape. So maybe we can increase, instead of 60, we make it 50 or 40, and then generate the mesh, so it will become denser. Or maybe we make it 60, generate, and then let's say we know already where the possible what call it buckling at the middle here. Then okay, so we add the mesh control for the face here, element face. We set to 40 or 40. Select, click this one, 40 mm. Oh no, we specify the elements number of anyway face here 60. We select only these 3, 1 2 3 like that. Then after that we right click, generate the mesh. So for this one only these 3 member. So then we can reduce, I mean specifically select the area that you want to highlight, then run the analysis. So it is not necessary to increase all the numbers of mesh, only specific one. So it's keep quite longer analysis because numbers of the what do you call it meshing, so more number of calculation time required. Done over there. Let me see, is there any deformation happen here? Maybe we close this one. Then is there any deformation happen? Oh, let me check, increase the option here. Maybe the deformation actual, no wonder. Let me set here. It's too far, too big. 5. Okay, and then check the deform. There is I think it's not so clear, deformation. Can see. Anyway, the contour here. Anyway, the linear buckling gives you the exaggerated deformation. Then here we can see that what you call it, this 60 degree of corrugated shape will not really given what you call it stiffening what you call it effect on the web. So then suggested in the code, NXD Eurocode 3.15, it's supposed to be 30 degree and the alpha. So then you can play around which one that maybe 30 degree is too what call it, and then if you want to reduce, and you have to be able, I mean, based on the analysis and then the finding here that we have to run the analysis, so there is the deal with between the material cost and then also the length of the what you call it, the welding and so on and so forth. Okay, so that's all for this video. Thank you.